So now you all are going to do the experiment. So are you all ready? Shall we? And get ready with your second set of chemicals, which has the white label on it. Pay attention. Get ready with your second set of chemicals, experiment number 2, having the white label on it. Hydrogen peroxide, the big bottle. Detergent solution. Food color, only if it is there on your table. Don't worry if it is not there on the table. You know why? And potassium iodide solution. And the measuring jar to perform the experiment. So are you all ready with your second set of chemicals? So shall we move on? You ready? Okay. So moving on to the first step, cleaning part, the good laboratory practice. You may please wash the measuring jar with water and the water bottle. Swirl it around to make sure it's clean and empty the content into the bucket which is there next to your table. So you're ready with the measuring jar? Shall we move on to the procedure? Ready to experience the tiranga? Okay. Moving on to your first step, pour the given H2O2 solution into the measuring jar. Your first step, pour hydrogen peroxide solution into the measuring jar. Now you can see hydrogen peroxide solution in the measuring jar. And with that, we move on to your second step. Add the detergent solution to it and swirl it around. Add the detergent solution to hydrogen peroxide and swirl it around well. Any change? Do you observe any change? No change. Swirl it around. Moving on to the third step. Your step number 3. Add the food color if it is there on your table. Others can just watch your friends pouring the food color to the measuring jar. If you have food color on your table, please pour it into the measuring jar. Now there is saffron on one side, there is white in the middle and green on the other side. You can look around. So that was your third step. Addition of food color to the measuring jar. Now what do you observe? You observe the color, right? And what do we have to add next? Is there an immediate reaction now? Hydrogen peroxide plus detergent plus color? No. So you are going to add the catalyst, which is potassium iodide. Your step number 4, addition of potassium iodide to the measuring jar. And please observe the tiranga or the tri-color of our national flag. Your step number 4, add potassium iodide solution to the measuring jar. Hydrogen peroxide, the detergent, the color, potassium iodide, the emerging signs of India. The song comes out presenting the emerging signs of India, the tiranga of our national flag. Friends, you have completed that reaction. Great. So now Since it is an exothermic reaction, please sit down. All of you please sit down. We'll wait for some time before cleaning. Now again, you must take your student report, the same old student report. You have filled the details of the first experiment. Now you're supposed to fill your observation about the second experiment and your conclusion for the second experiment. Students, write down the observation and conclusion for your second experiment.
So that is outside the
yeah.
Make sure your name, your class, your school is all there. Your observations for experiment number 1 is there. Your observation for experiment number 2 is there on the paper. And your conclusions about the 2 experiments.
It is a positive catalyst.
Better read the things before submitting. Read the
पहले 2 बार प्रैक्टिस कर चुका, देन नो व्हाट टू डू। ट्रेन करना नहीं, उसको मत करो।
Now I hope you all have with you a completely filled student report having your name, your class, your school, your observations for experiment number 1 and 2, and your conclusions for the 2 experiments. Is it done? So what next? Before that, I want all of you to hand over the reports to your teachers, and the teachers are going to hand over the reports to the stewards. I request all the teachers, please collect the student reports from students and hand it over to the stewards. We still have work to do. Before that, I request all the teachers to collect the student reports from students and hand it over to the stewards. So I hope all the teachers have collected the student report. I request you all to please hand it over to the stewards. Now, by the time they do that, I want each one of you from one group to do the cleaning part. Now you can clean the measuring jar with water and wash bottle and empty the contents of measuring jar into the bucket available next to your table. All of the students, please sit down. Just the person washing the wash bottle, who is washing the measuring jar, you need to stand up. All of the students, sit down. Clean it well. And empty the contents of the measuring jar into the bucket available next. Students, please remain silent. We come into the end of it. I request all of you to please remain silent. What you're doing now is a good laboratory practice. And you must always keep in mind when you enter a lab. Students, please remain silent.
Not the laptop.
You can be seated.
Huh? Where is the stop clock? Oh, it is there.
In proper police custody. Literally.
Yes, Stanley. Go ahead.
Now, to conclude, we have performed 2 experiments today. Experiment number 1, which was the discoloration of methyl blue by hydrogen peroxide using Fe2 as the catalyst. And experiment number 2, which was the decomposition of hydrogen peroxide with iodide as the catalyst. In both the experiments, it's the catalyst that brings in the magic. So, a catalyst is like adding a bit of magic to a chemical reaction, or in your words, a catalyst is like a wizard, right? Yes, so with that, we are done with both the experiments. And as you all know, records are meant to be broken. We would like to thank the holders of the last record, Royal Society of Chemistry, for setting up such a record which motivates us to live. We hope that creating this new record, we have inspired our younger generations to have a go at it in the near future. And above all, we hope it is an inspiration for more and more students to take up the exciting discipline of science and create new records which will make our great country proud. I am proud to have you here with you. My heartiest congratulations and a big thank you to all of you for making this happen. Thank you all once again, and here we end the lesson. Thank you.
First, 10343.
Zoom in, zoom.
Dear children, please be seated. You have been part and parcel of such a huge mega event that we planned. So for further few more minutes, I will request all of you to cooperate. There are few more procedures which are left, so I will strongly request, please be seated. I must acknowledge, I must admire every one of you. Being such a perfect, the most critical part of it, you were all obedient. I am surprised. As an organizer, I salute every one of you. All 2,000 of you. Not even a single apparatus was being asked to be replaced. This is amazing. This is amazing. We are not sure whether we will make it or not. We have done our efforts. We have done our efforts. Every student have collected the reports that will be given to the witness now. All that procedure, let's wait for a few more days. Let us see how much accurately we performed. Let the authorities evaluate our content, the procedure. But I am telling you, as a part of an organizer, I am really amazed to see all 2,000 students beautifully, well organized, well maintained. I salute you once again. So I request you, just cooperate for another 10 more minutes. To disappear from this place, we will have to follow the another procedure. Because if I say the ends here, we will start to move from one direction and at everyone at a time. That will not look nice. For every one of you, for every teacher of the 40 schools, the food arrangement has been done. So as much meticulously, as precisely you've done, you cooperated with us, I will strongly request every one of you to be again cooperating with us. I will just request the witnesses, if they can allow to move out of the campus, then I will start making them to move. But before that, let me request you all of you, we will follow some procedures. One school along with the 2 teachers will move ahead. All the teachers, while going out, there is a table, registration table, where all the teachers need to collect their reimbursement. All the students will proceed again to the Kendriya Vidyalaya inside the IIT campus. The moment you start from here, you can call your driver to come and pick you from Kendriya Vidyalaya. All the lunch boxes, I will strongly request you carry it yourself. Don't try to eat it here because it will take a long time and it will be a huge kind of a problem for the arrangements. The lunch boxes are in the Kendriya Vidyalaya. I will request the teachers to just collect your reimbursement and with the same manner, with the same meticulousness, seriousness, follow in the queue. Collect your lunch boxes. So the moment I ask team to leave the place, call your driver, let the driver reach the Kendriya Vidyalaya. By the time you will also reach Kendriya Vidyalaya, collect the lunch boxes, get into the buses. All the transport reimbursement from the organizer's point of view, I hope you have deposited all your bills to a person who was at Kendriya Vidyalaya. If you have not, the persons are waiting outside. If some of you have left out, please give it to him and he will make the arrangements. Let me tell you again, our teachers or the schools, all the logistic part of the reimbursements, of the travels, of the buses will come to you. I will again be sending the details through emails. So as far as the transportation is concerned, the job is done. Now I will request team number 40. Team number 40 to please move from here and exit. Dr. Girish, where is Dr. Girish? Exit number, exit this way, that way.
Liquids which are immiscible, maybe like water and oil. So they are said to be in two different phases or a single phase. They're said to be in two different phases, right? So that's about phase. Now let's see what's homogeneous and heterogeneous catalyst. Homogeneous, from the word you know, when the reactants and the catalysts are in the same phase, that process, that catalytic process is called as homogeneous catalysis. But when the reactants and the catalysts are in two different phases, we call it as heterogeneous catalysis. Now heterogeneous catalysis is also called as contact or surface catalysis. Now moving on to some of the examples of homogeneous and heterogeneous catalysis. The classic example for homogeneous catalysis is the decomposition of hydrogen peroxide by iodide, and that's the reaction we are going to perform today, right? Here, both hydrogen peroxide and potassium iodide, the catalysts, are in the aqueous phase, and so that catalysis is called as homogeneous catalysis. Now here are some examples for heterogeneous catalysis. As you can see there, the synthesis of ammonia using nitrogen and hydrogen with iron as catalyst. That's a combination of solid and gas. Whereas we have hydrogenation of fatty acids with nickel as catalyst. Here it is a solid liquid combination. This reaction is also used for the production of margarine. Then we have the hydroformylation of propene with rhodium catalyst. Here it's two immiscible liquid phases. The catalyst in the aqueous phase, whereas the reactants and the products are in the non-aqueous phase. So that is again an example for heterogeneous catalysis. Now moving on to the next classification, which is based on the rate of the reaction. Based on the rate, they are classified into positive and negative catalysts. What do you mean by positive? That they increase the rate of the reaction. Whereas negative catalysts, what do? They decrease the rate of the reaction. So let's see how that works. A positive catalyst, it decreases the activation energy by accepting a smaller pathway so that the rate is increased. As you can see there in the diagram, it accepts a smaller pathway, thereby decreasing the activation energy. And if the activation energy is lowered, what happens? The rate is increased. And that's how a positive catalyst works. Now the best example for a positive catalyst is the biological catalyst, which is enzyme. Most of the chemical reactions that take place in human body and also in other living organisms are very high energy reactions that occur extremely slowly. So to increase the rate of such reactions, we'll have to add we can't add catalyst, but the enzymes work there. An example for that is in the absence of a catalyst, it takes several weeks for starch to hydrolyze to glucose. And a trace amount of the enzyme thiolin found in human saliva is the one which accelerates the reaction so that starch can be digested. So this itself is the best example to show the effect and the importance of a catalyst. Now here are some other examples of positive catalyst, like the decomposition of potassium chlorate using manganese dioxide as the catalyst. Then we have the oxidation of sulfur dioxide using vanadium pentoxide as the catalyst. And also in the Deacon's process, the initial step is a generation of chlorine, and for that step you require a catalyst, that is copper chloride. Now what are negative catalysts? Negative catalysts are also called as inhibitors. Do you know why? Because they decrease the rate of reaction. Now how do they work? They work by taking a longer pathway and increasing the activation energy, thereby decreasing the rate of the reaction. As you can see, that it takes a longer pathway, and therefore the activation energy is also increased. Here's an example for a negative catalyst. Phosphoric acid can act as a negative catalyst for the decomposition of hydrogen peroxide. And we all know that we're going to perform today's experiment. One of the experiments is the decomposition of hydrogen peroxide, and this experiment can also be catalyzed using a positive catalyst. See the difference? A same reaction being catalyzed using a positive and a negative catalyst. Here phosphoric acid acts as a negative catalyst, whereas in our reaction, it is going to act as a positive catalyst. Which one? Potassium iodide is going to act as a positive catalyst. Now, hearing the word negative, don't get this feeling that these catalysts have a total negative effect. There are certain reactions which must take place at a slower rate. And for such reactions, we can't add positive catalysts. So what do? We have to add negative catalysts. Here's the example. To decrease the ignition of petrol vapors, you add tetraethyl lead to petrol. So here, tetraethyl lead acts as a negative catalyst. And if we don't add this, what will happen? The petrol vapors will ignite even early than expected, resulting in the wastage of fuel. So in order to improve the fuel efficiency and the performance of the vehicle, we have to add tetraethyl lead. And this is called as leaded petrol. Now you can see three terms on the screen: catalytic promoters, catalytic poisons, and optimum temperature. Let's see the relevance and importance of these three terms in the topic catalysis. Catalytic promoters, they are substances which themselves are not catalysts, but when mixed in small quantities with catalyst, they increase the efficiency of the catalyst. Understood? They are not catalysts, but only when present with the catalyst, they can increase the efficiency of the catalyst. Therefore, they are also called as activators. They are called as promoters or activators. As we saw in the Haber process, we add potassium oxide to it, and potassium oxide increases the efficiency of the ion catalyst. Therefore, potassium oxide is called as a promoter or an activator. Coming to catalytic poisons, they are substances which act the opposite way. They destroy the activity of the catalyst by their presence. Again, we can take the example of Haber process. If you add CO or H2S to it, it destroys the activity of ion catalyst. Now again, like I said for negative catalyst, by hearing the term poison, you should not get this feeling that they are not useful in catalysis. They are extremely useful in catalysis. Why? Let's see how. In the reduction of acetylene to ethene with palladium catalyst, what we do is we poison palladium catalyst with lead 2 acetate. Now, lead 2 acetate, what it does is, at a stage, it deactivates the catalyst. And if we don't deactivate the catalyst, what happens is, the reaction further reduces. That is, ethene further reduces to ethane. And that's not what we want. We want the reaction to stop at ethene. So in order to stop the reaction at ethene, what we do is we poison the catalyst. And here the example is lead 2 acetate. Now coming to optimum temperature. The The change of temperature alters the rate of catalytic reaction as it does for the same reaction in the absence of a catalyst. For example, if we increase the temperature, the catalytic power of a catalyst also increases. But after a particular temperature, the power begins to decrease. And that particular temperature from where the power begins to decrease is called as the optimum temperature. And for every catalyst, there is an optimum temperature. Now, coming to the experiments that we're going to perform today, experiment number 1, which is catalytic discoloration of methylene blue by hydrogen peroxide, and the second experiment, the catalytic decomposition of hydrogen peroxide. In the first experiment, hydrogen peroxide being a strong oxidizer, it's going to oxidize methylene blue. But that reaction is a very slow process. So in order to increase the rate of that reaction, we're going to add a catalyst to it. And the catalyst that is being added is iron. So in the presence of iron catalyst, the reaction takes place at a faster rate. In the second experiment, that is the catalytic decomposition of hydrogen peroxide, it's basically the decomposition of hydrogen peroxide, which again is a very slow process. So we have to increase the rate. In order to increase the rate, we'll add a catalyst, and the catalyst added is potassium iodide. The iodide ion from potassium iodide acts as the catalyst here. And in this reaction, we also add some detergent solution and some color just to make the reaction more visible. Okay? Now in these two experiments, you can see something in common. What is that? Yes, hydrogen peroxide or H2O2. So let's get to know more about hydrogen peroxide. It ranks up there as one of the best household remedies. And it is one of the few miracle substances still available to the general public. It is highly safe, readily available, and dirt cheap. And best of all, it works. Hydrogen peroxide can put extra oxygen into your blood. So if you can get oxygen into the blood cheaply and safely, maybe diseases like cancer, which doesn't like oxygen, and also emphysema, AIDS, and many other terrible diseases can be treated effectively. Now, intravenous hydrogen peroxide can rapidly relieve allergic reactions, influenza symptoms, and acute viral infections. And because of all these medical advantages of hydrogen peroxide is also called as a medical miracle. Now, did you know that you probably had your first sip of hydrogen peroxide shortly after you took a first breath? Yes, that's right. The mother's milk, especially colostrum, contains high concentrations of hydrogen peroxide. And the main function of mother's milk is to activate or stimulate the immune system in infants. And the fact that it contains abnormally high concentrations of hydrogen peroxide definitely makes sense. Hydrogen peroxide was first described in 1818 by Louis Jacques Thénard. It is a colorless liquid. It acts as a strong oxidizer, a bleaching agent, and also a disinfectant. And when present in the concentrated form, it is used as a propellant in rockets. Now, you can see some of the reactions of hydrogen peroxide. Hydrogen peroxide undergoes decomposition reaction, redox reaction, organic reaction, and also it can act as a precursor for other peroxides. The decomposition reaction of hydrogen peroxide is a very common process. As you can see there, hydrogen peroxide decomposes to form water molecules and also oxygen. But like I said before, this process is a very slow process. So in order to increase the rate of this reaction, what can we do? We can add a catalyst to it. Now, we know we have two experiments for the day, and in both the experiments we have hydrogen peroxide in common. In the first experiment, the hydrogen peroxide is going to act as a strong oxidizer, whereas in the second experiment it is going to decompose. Let's see how. The first experiment, which is the discoloration of methylene blue by hydrogen peroxide. This reaction is also called as Fenton's reaction. It was discovered by Henry John Holtzman Fenton in the 1890s, and the classical Fenton's reagent is hydrogen peroxide combined with an iron catalyst. Fenton's was not widely used until 1930 when the reaction was suggested by Haber and Weiss. They postulated that the successful reaction generates the highly reactive hydroxyl radical, the OH radical. As you can see there in the diagram, hydrogen peroxide in the presence of iron catalyst produces the powerful oxidizer hydroxyl radical. And Fenton's reagent has been widely used to destroy organic compounds. Now, what's the chemistry behind this reaction? Like I said before, hydrogen peroxide being a strong oxidizer, it can oxidize methylene blue. But that reaction is going to be very slow. So we add a catalyst to it, and the catalyst added is Fe2+. And hydrogen peroxide oxidizes methylene blue at a faster rate in the presence of Fe2+, resulting in the discoloration of methylene blue. And it is the strong oxidizing property of the hydroxyl radical that causes the degradation of the dye. Now, here are some of the applications of Fenton's chemistry. It's widely used to treat a variety of complex industrial wastes. It's used in the soil and the groundwater remediation, heavy metal contaminated wastewater, to destroy organic resins in radioactive contaminated sludge, in the COD and BOD reduction, and also for odor control. Now coming to the second experiment, which is the catalytic decomposition of hydrogen peroxide. This experiment is also called as the elephant toothpaste experiment. Do you know why? Because in this experiment, you are going to observe a tower of foam emerging from a measuring jar that resembles a huge stream of paste. So that's the reason why this experiment is also called as the elephant toothpaste experiment. Now, what is this experiment actually? What is the chemistry behind it? This is also a decomposition of hydrogen peroxide. Like I said before, it is a very slow process. So we add a catalyst to it, and the catalyst added is potassium iodide. It's the iodide ion from potassium iodide that acts as the catalyst here. It speeds up the reaction without itself being consumed in the reaction. Now here's the mechanism. The iodide ion changes the mechanism by which the reaction occurs as follows. Hydrogen peroxide plus I minus gives OI minus plus water, and it further reacts with hydrogen peroxide giving I minus plus water plus the oxygen. And it's the evolution of oxygen that causes the bubbles to come up. Also remember, this reaction is exothermic, so the foam produced is going to be slightly hot. Now what's actually happening here? As a small amount of hydrogen peroxide generates a large volume of oxygen, the oxygen quickly pushes out of the container. And like I said before, we are going to add detergent solution to it, and because of the detergent solution, the soapy water traps the oxygen, creating the bubbles, and turns into the foam. Now I think we're done with the theory, so shall we move on to the performance of the experiments? Friends, now I think it is time for you all to perform the experiments. But before that, wait, we still have time. All of you, get ready, get connected, work together and be prepared to experience the magic of chemistry. And now what I want you to do is watch the demo for experiment number 1. You are not going to perform now, you're only going to watch the demo for experiment number 1. It's only after they perform, you will perform, and I'll tell you when to perform. So now you're going to watch them. We have the instructors here and they're going to perform the first experiment for you. Have a clear look. Experiment number 1, the discoloration of methylene blue by hydrogen peroxide. The chemicals required are methylene blue solution, hydrogen peroxide, H2O2 present in the small bottle. You again have H2O2 in the bigger bottle for the second experiment. Then we have ferrous sulfate salts. And we also have a beaker to perform the experiment. Now what you have to remember is the first set of chemicals will have a green label on it. The first set of chemicals will have a green label on it. So shall we see how these chemicals were prepared? We have taken 10 ml of 30% hydrogen peroxide, that is H2O2, and methylene blue solution was prepared by adding 1 drop of methylene blue reagent in about 20 ml of water, and we have taken 50 milligram of ferrous sulfate salt. So, ready to see the experiment? So shall we move on to the procedure? What do you think will be the first procedure? The washing of the apparatus, which is a good laboratory practice. Washing of the apparatus is very important before you do the experiment and after you perform the experiment, because this is a good laboratory practice. So the instructors are going to wash the beaker with the water in the wash bottle. Just swirl to make sure the beaker is clean and empty the contents into the bucket available next to you. Here we're going to drop it down because we have the bucket down there. So moving on to the procedure, step 1. Take the methylene blue solution into the beaker. You can see there, now the methylene blue solution is in the beaker. Shall we move on to the next step? Step 2. Add the given H2O2, the hydrogen peroxide, to this methylene blue solution. You can see the instructors have added hydrogen peroxide to the methylene blue solution. Is there a reaction there? Actually, there is a reaction there, but the process is very slow. It's just that it's not visible to us. So what do we do to increase the rate of the reaction? We are going to add the catalyst, which is step 3. Now add the given ferrous sulfate salt to this solution and swirl well. Yes. Now you are going to observe a rapid color change. Why is it? It's because of the presence of the iron catalyst. It increases the rate of the reaction, and hydrogen peroxide oxidizes methylene blue at a faster rate in the presence of the catalyst, Fe2+. So now, are we done with the reaction? No. We have one more step there, and what is that? The cleaning part. Again, a good laboratory practice. They're going to empty the contents of the beaker into the bucket, which is there next to them, and wash the beaker with the water in the wash bottle. So now the beaker is clean and we are done with the demo of the first experiment. So what they're going to do is keep the first set of chemicals aside. Now don't you want to perform? Now it's your turn. Friends, are you all ready? Ready to perform the first experiment? So shall we start? Okay, students, get ready with your first set of chemicals, which contains a green label. Please pay attention. Your first set of chemicals contains a green label. I'm going to say the chemicals. You have methylene blue solution. Can I see the methylene blue solution? Yes. Then you have hydrogen peroxide with the green label, H2O2 with the green label. Then we have ferrous sulfate salts. Can I see somebody? Okay, we have the ferrous sulfate salts, and what else do we need? We need the beaker to perform the experiment. So, there's the beaker. Yes, I can see that. Now I hope all of you are ready with your first set of apparatus and chemicals. Students, you've been sitting for quite a long time, so can you all stand up? We're going to perform the experiment. You're not going to sit down. stand up and be active. You are going to do the first experiment now. So be ready. We're moving on to the first step, which is the cleaning part. I request all of you to clean the beaker with the water in the wash bottle available on your table. Wash the beaker, swirl it around and make sure it's clean with the water in the wash bottle. Now, one of you from each group can empty the contents of the beaker to the bucket which is there next to you. Just one. One from each group may empty the contents of the beaker to the bucket which is there next to your table. Are you all done? Ready? Okay, shall we move on to the procedure? All right, moving on to step 1. Take the methylene blue solution into the beaker. All students take the methylene blue solution into the beaker. Can I see there up? Can I see the methylene? Okay, all of you have taken the methylene blue solution into the beaker? So shall we move on to the next step? Your step 2. Add the given hydrogen peroxide, that is H2O2 with the green label, to this methylene blue solution. Add H2O2 to this methylene blue solution. Please make sure you have taken the one with the green label. I can see hands up there. Now swirl well, see if there's any change. But is there a reaction taking place there? Yes, there is a reaction taking place there, but you are not seeing a visible change. So what can we do now to see a visible change? And what's the catalyst? Yes, so moving on to step 3. Add the given ferrous sulfate salt to this solution and swirl well. Students, add the given ferrous sulfate salt and swirl well. Yes, I want to see the color change. Can we see the color change? Is there a rapid color change? Or is it still the blue color that you're seeing? No. We have observed a rapid color change. Why is it? It's because of the presence of Fe2+, which acts as a catalyst here. What does it do? It increases the rate of the reaction. Which reaction? The oxidation of methylene blue by hydrogen peroxide. So are we done with the first experiment? No, you still have one duty to do. What is that? The washing part. Yes, the good laboratory practice. You should never forget this. Empty the contents of the beaker to the bucket which is there next to you.
Good laboratory practice. Good laboratory practice.
I hope all of you know that this is a good laboratory practice which all of you must follow when you enter the lab. Now wash the beaker with the water in the wash bottle. And once again you can empty the contents into the bucket which is there next to your table. So are you all done with the washing parts? So now what can we do? Move on to the second experiment. Are you going to perform or the official instructor is going to perform? We'll see the demo for the second experiment. But before that, you have one more duty to do. You'll have a student report. You're supposed to write down the student report, which is going to look like this. You have a student report with you. Each and every one of you must write down the student report. In the student report, you're supposed to write down your name, your class, your school, and your observation of the first experiment, just the first experiment, and also write down the conclusion of the first experiment, leaving space for the second experiment. Now you can sit down. Now you can sit down and write the student's report. Remember, you must leave space in the conclusion part to write the conclusion about the second experiment. Your student report is with you. You must write down your name, your class, your school, your observation for experiment number 1, and your conclusion for experiment number 1. But note, you must leave space to write down the conclusion for experiment number 2 also. class, your school, legibly. Write it neatly. Write down your observations for the first experiment and also the conclusion for the first experiment, leaving space for the second experiment's conclusion. So are you all ready? Once again I repeat, make sure your name, your class, your school is all very clear. And write down your observations for experiment number 1 and your conclusion for experiment number 1, leaving space for experiment number 2. So, you ready?